polynomials by Peter Ivanov, speaker, Liam Pavlovich, and Emanuele.
Thank you. So I'll be talking about correlation bounds against low degree polynomials. So we just heard in Junji's talk and some other nice talks in this conference that have studied correlation bounds for other restricted models of computation. So in this talk, we'll be focusing on low degree polynomials over F2. And just as correlation bounds serve as kind of a benchmark of our understanding. If we have a weak complexity class, we want to say we would like to be able to prove strong correlation bounds, or that a function can approximate it, which kind of formally shows that this class is indeed weak. And some problems that you can consider to be on the frontier of P versus NP, the famous circular lower bounds, proving explicit rigid matrices, number on forehead multi-party communication lower bounds. All these problems require progress in correlation bounds for exactly low degree polynomials to be able to say something new. And another work, kind of a different vein, but there's a recent line of work showing that if you have some Fourier growth bounds on low degree polynomials, then you get new PRGs. And it turns out these works also require new correlation bounds. So I'll formally set this up in a couple of slides, but to borrow a couple images from my advisor, there's this, you can think of this pyramid. The traditional view is you have all these problems, correlation bounds, matrix rigidity at the bottom of the pyramid that we have to get through towards proving P equals NP. Well, maybe we can flip this pyramid and think of correlation bounds for low degree polynomials as being the first thing we should think about. Okay, so some definitions and related works. So we have a function f and p, and the correlation is just a probability that they're equal to each other. If you take p to be the constant zero function, and if f is balanced, which we can just assume it is, then you get correlation 1/2, because the zero function will agree on the zero outputs of f. So we're interested in how much advantage we can get above 1/2. So our advantage will denote epsilon. Some classical results by Rozbor-Smolinski in the 80s, they showed that you have correlation d over square root n, and their hard function was the majority function. And another work showed that for generalized inner product, or alternatively the mod 3 function, you get correlation bounds of 2 to the minus n over 2 to the d. So I just want to talk about this parameter so we understand. So this epsilon is very strong for small d, but it loses meaning once you get towards d, towards about log n. And the first correlation bound says something non-trivial for d equals log n, but it may seem like not much, the upper problem that's stated right after. It's only log n factor, but as a matter of fact, we haven't been able to improve this since the 80s. And any progress here would be extremely interesting. And yeah, a clean open problem that you can think about in your free time is find some f in NP, which has correlation 1 over square root n for d equals log n. So just a little bit improvement. And answering this question is, progress on this question requires progress. Progress on the previous problems in the pyramid needs progress on this problem. Okay, there's an exciting recent work by CHLZ. They gave new correlation bounds for majority XOR majority, and in fact, the results generalize to a larger class of functions, resilient functions, which I won't get into. But this is especially interesting because you can think of XOR bounds as being one approach towards proving correlation bounds. So they defined this local correlation in an older paper. Basically, you should think of this quantity as the probability that the function is fixed after you uniformly assign variables to S over line. So if it's large, that means the function is fixed after you uniformly assign variables to S overline, and otherwise the bias will be close to the initial bias of the function. And they show that for low degree polynomials, this S won't be too large. You get an exponential bound in this degree. And this implied the correlation bounds I first mentioned for F equals majority, XOR majority. And they conjectured that, in fact, S at most polynomial in D would give you, would work, and this would give you very exciting new correlation bounds. This would solve the open problem on the previous slide and much more. So our first result is we give a counterexample to their conjecture. We show that basically what they prove is best possible. And the counterexample is simple. Actually, you just take the tribes function and, yeah, good old tribes to the rescue. And you can show that it's fixed with high probability, even on large sets. And this is, I'll just say in one line, it's because as long as S isn't too big, there will be some terms you don't touch. And those terms will be 1 with constant probability, which fixes the rest of the tribes to 1. And I should say tribe for those that don't know. Tribes is just an orient circuit that's read once, so very basic. And then we can just take a polynomial approximation to tribes, and it will have the same property as the initial tribes function, and this P gives us the counterexample to the conjecture. So the message is their approach won't go further than what they proved, so we have to think of other ways to get new correlation bounds. All right, and some additional questions we can ask, given that we ruled out this approach and that we've been stuck on proving correlation bounds for so long. For certain candidate heart functions F, can we provide more information? Can we say anything new? One question that we can ask is whether we can give exact bounds for this correlation, for this epsilon parameter. And a motivating work by Green back in 2004 showed that you can for the parity function and polynomials over mod 3. And this is a pretty basic setting, and even though it's a basic setting, people have been trying to extend this for a while, and there hasn't been any progress up until now. Another question you can ask is for the mod k function, whether symmetric polynomials maximize the correlation. And I think it's a natural thing to consider because mod k functions are symmetric in some sense. However, the polynomials in Green, the maximal polynomials in Green's paper, were not symmetric. So the current evidence to this question is negative. Excuse me, I'll get some water. My mouth is a little dry. You know, I heard once that a good talk should follow 3 rules. The first rule is you should tell a joke. The second rule is you should give a proof. And the third rule is that the first and the second should not be the same. So we get into the proof, but unfortunately I didn't prepare a joke. But that's okay. So our main result is that, well, first we conjecture that symmetric polynomials do maximize correlation with mod k. And if this conjecture is true, if you can show this is true, then this would answer the open question from before and tell us much more, just because we have exact correlation. You can compute exact correlation bounds for symmetric polynomials and the mod k function. And we proved that this is true for degree 2 polynomials. And we have some partial results for degree 3. Okay, so our theorem is that the correlation of mod 3 with any quadratic polynomial p is at most the correlation of mod 3 with the quadratic symmetric polynomial s. Okay, and we do this by looking in terms of the correlation of the derivatives. So we're looking at the partial derivatives because we're dealing with Boolean functions. And just one thing to note, when we take the derivative of p, it becomes a linear polynomial because we started with a quadratic. And there will be some structure there to play with. And this will be important in the proof. So our first step is a standard step in many other papers on this topic. We can write the square of the correlation in terms of the correlation of the derivative of p and the derivative of mod 3. Okay. So I define this quantity CYP, which is just the inner term here. And so in the rest of the proof, we'll just be showing that this expected CYP is at most expected CYS. Okay. And the key lemma, I guess the first thing we showed in the proof, which kind of, once we had this, we were able to get the rest of it down, is that under certain conditions, which I won't get into, as long as one bit is fixed to 0 in y, then good things happen. And intuitively, this is just because when you have one bit fixed to 0 in y, you can get a hanging linear variable in the derivative of py for a lot of these y. And our second lemma is that to conclude, our last lemma that we use will just be that under certain conditions, and you have enough ones, basically, that CYP will be at most CYS as well. Okay. So following these two lemmas, the rest of the proof becomes natural. You just start with expected CYP, and then you just condition on the first variable. So as soon as you have some variable that's set to 0, we can use the key lemma. But then we still have to deal with the remainder term. But the remainder term we can just open up again. And we go on until we can use the second lemma from the past. So once there's some conditions that are held on the last term, then we use the second lemma. All right, and so by the key lemma, all of the places where we have at least one bit set to 0, we're happy. And then we use the second lemma and we're happy with the last term too. But we can, I'll say just to be clear, we can't use the second lemma just at the very beginning. You need some conditions to hold. And these conditions will only hold after you open this up for a bit. All right, so now I'll go over a sketch, or try to convey at least the main ideas behind the key lemma. And we'll do a simpler case, but I guess there's some more logic and some more annoying technical details to do in the general case, but for this case, it's a little simpler. So we can show this inequality whenever x1, x2, the quadratic term appears in P. And I mentioned this a little bit earlier, but the main idea is that x2 will appear in the linear derivative py for many of these y that satisfy this condition. But the mod 3 derivative will only depend on the xi where yi is set to 1. Okay? So mod 3 doesn't depend on x2, but this py will, and this will just make the correlation 0. So this will cancel out a lot of terms. And this matches how CYS behaves. So the correlation of the quadratic symmetric has a very nice structure, and this just follows by looking at derivatives of the quadratic symmetric. And so we get this nice expression for the sum of CYS. Half of them will be 0, while the other half, where the weight of the remainder bits is odd, we get this sigma to the y, where sigma is just some constant that, yeah, you should think of sigma as just a constant, less than 1. Okay, and yeah, you take because of restriction 1, 0, y, the behavior will match the behavior we just saw on the previous slide. All right, we have this upper bound for any y, which is not hard to show, and we also have this property that will be equal to 0 whenever the weight on a certain subset of y is even. And this subset is just the variables that appear with x1 in some quadratic term. So basically, this just subset, the weight of the subset determines whether x2 appears in the derivative or not. And because the y2 is set to 0, we get cancellation and it'll be 0. All right, so then our sum simplifies based on the y whose weight is odd on yt. Okay, so this is just the specialized case of the key lemma restated. Based on the last two slides, the CYP turns into this expression, and the CYS turns into this expression. To conclude, we just condition on the parity of the weight on the remaining bits of y. Okay, and so there's two terms in this. The other terms will just cancel out. But it remains to show this expression, which you can show by just plugging in formulas for binomial sums. So just the sum over even weight strings is a little bit bigger than the sum of odd weight strings. So that's what allows you to conclude in this other case. All right, and some additional things I want to say about our proof. When we prove the key lemma, in the first step, actually, when we have y equal, when the first bit is just set to 0, we show a strict inequality, or we show a buffer through this delta. So we get some wiggle room, which actually is crucial in our proof, because in our last step, there will be some loss, actually. So this first step offsets that loss. And even though we have this inexact result, we still get exact correlation bounds in the end. And there's also a cute application of the handshake lemma that we need in the proof of the key lemma. You can think of the derivatives in terms of graphs, and then you can just get a slight improvement in one of the bounds. And yeah, it's pretty fun. Okay, so that was the end of the proof. So back to summarizing everything. So correlation bounds is just a fundamental problem in its own right, but it also is very motivated because a lot of other problems reduce to proving new correlation bounds. Okay, and so for our first result, we rule out this nice approach of CH-HLZ, showing that we need to come up with new approaches. We conjecture that, okay, one approach we can consider is that symmetric polynomials maximize correlation with mod k. We proved this conjecture for degree 2 polynomials. We have some partial results for degree 3. So the most natural open problem from this would be to prove it for degree 3, or just to show or disprove the conjecture for any degree, really. I think it'd be interesting. Yeah, I thought about it a little, but it's just very not clear how one might show this. Okay. That's it. Thank you very much.
What was the joke?
I think those three rules were my joke, to be honest. Yeah.
So what's the correlation bound that you get if the conjecture is true? Can you just remind us?
Yeah. Yeah, so you get exponential in n, even for a large degree. So we just wanted, we wanted 1 over square root n, even for degree log n, but if the conjecture is true, you get 2 to the minus omega n for basically, I think up to any d, except for d equals n, but I think up to some polynomial d, like square root d, or square root n, I mean.
Let's thank all the speakers. Okay.